Okay, welcome to this lesson where we're going to take a look and introduce systems of equations. And this is dealing with linear equations or linear functions particularly. But we're going to take it one step further on the linear equations and look what happens when we have what we call a system. And a system, just to kind of start off a little bit, a system is when we have multiple equations as a part of a problem. And we're going to look mostly at contextual problems when it comes to these equations. So first of all, let's just do a quick little review of linear functions. What is a linear function? Well, reminder that a linear function is a relationship between the independent and dependent variables, or characterized as x or y according to x. A linear function is two variables which are in a relationship together, and the equation is given to describe the relationship. Okay. So here's another one again. These relationships can be thought of as an equation, which uses the variables x and y. Okay. Now I've titled them as independent and dependent. We haven't talked a lot about that in class, but they are two variables which are in relationship to each other, and the equation describes the relationship. Okay? It describes how the relationship works and describes what is going on with the relationship. So that's a couple of little things about the equation. Now, in the previous lessons that we've taken a look at, we have learned about two forms of describing lines. The first one being graphic form, and the second one being slope point form. These are two ways of creating an equation and determining what it might look like based on our rate of change, such as being the slope, as well as some reference point that we have in there. In the first one, in graphic form, that reference point is our y-intercept. And in the second one, the reference point is any other point that might be on the graph, okay, or on our line, some point that satisfies the relationship. So we can use these two. Now we could also create an equation with just random, in not necessarily these forms. So if we can see that, we can understand if numbers are added together or subtracted or multiplied, we could use that to represent our function as well. Now, any equation which relates to an independent variable, or x, and dependent variable, y, to a value can be a linear function as long as we have a singular x and a singular y that is a part of it. Okay, no exponents. Don't worry, in grade 10, we don't talk about any exponents. This is a grade 10 lesson. In grade 11, we're going to get into exponents. And that's the fun stuff. Yeah. Well, for some people. So what we're looking at here is the two, or the functions that deal with an x and a y, and they are linear. The pattern goes up or down by a consistent amount, and it becomes a straight line when we graph it out. Now, a line, okay, on a graph can be described as a function as well. It can be made using the slope and any point along the line. Remember that if we have 2 points, okay, any 2 points on a line, we can find the slope. We can also find the slope in, let's say, a contextual question if we're given the rate of change. So how something is changing each time. Again, it will be a consistent amount. That's going to be our slope, or the rate of change. Some problems deal with two variables which equal a solution. These, again, as I mentioned before, are a little bit different form, but they can still represent a linear function, and we can maybe put them in what's called standard or general form as a way of describing them. All right, let's take a look at an example. We're going to try to look at a simple example to start, and then kind of build our way from there. What are we expecting from our examples? In the example I'm going to give here, we have two numbers which add to 16. We want to create a formula to represent the relationship, and then we want to graph the function out. So when we are talking about any question, especially when we're dealing with context, and this one has a little bit of it, the first thing we need to do is we have to define our variables. What do the x and y represent? Now we do this because we want to know if we have an x value, what is that x value representing? If I tell you that there are 17 kids wearing hats in class, well, that sounds a little bit high actually, but that's okay. If there are 17 kids wearing hats in class, what does that represent? Is that our x value or is that our y value? And it's important that everybody knows that. So that's why we have to define our variables at the start. Okay, so we always have to define our variables at the start. In this case, we're just told two numbers add to 16. So we can say that x is going to be our first number and y is going to be our second number. Now I could also tell you that if the second number is 12, what does the first number have to be? Oh, we can figure that out, right? Or if the first number is 3, what does the second number have to be? Again, we can solve for that. But we're given that context, so when we describe a number, we know which part it's going to be. Second step in here is we want to create an equation to represent our relationship. Now, in this case here, we're going up by, we're not really told a rate of change. We're just told that we have two numbers, x and y, which add up to 16. So we can write it out as x plus y equals 16. This one doesn't follow graphic form. It doesn't follow slope point form. It's more of a standard form question here, where we're just given some adding on one side and then we have an answer on the other side. So this is, again, another way of writing it out. This is where we would come through with a little bit more what we call logical reasoning method of writing it out, which is maybe simpler for some, but you need to be able to see the patterns that are happening. All right, now, as a part of this, domain and range, I always like to put that in there because I want you to start seeing that domain and range. Which x values are possible? Well, can we use negative numbers? Yeah, we can. Can we have decimals? For sure we can. Okay, really, any number does work in this situation for x, okay, because we could add negative infinity and positive infinity plus 16, and we're going to get a total of 16. Okay, so our domain and range are going to look a little bit like this. We're going to have x is all real numbers and y is all real numbers because every single value works in this situation. Okay, every single value works in this situation. Okay, now let's graph this out. What is it going to look like? Well, I have a little graph here. I've labeled it. I have my x and y axes. I've labeled them. I'm going up by 2 each time, and I think this should be big enough that we can put it together. I hope so. I prepared the slideshow, so it should be good enough. Now, what are we going to do? Well, because of the way that the equation is, sometimes it's nice to create a table of values. So what two numbers add up to 16? Well, 0 and 16 do, 4 and 12, 8 and 8, 12 and 4, 16 and 0, and there's a whole bunch more options in between there, but these are 5 good ones. If we take these and we plot them on the graph, and they look a little bit like this as they show up, you'll notice that they follow a really nice straight line, which we can put through there. Now this line also represents that every single point in between there is going to work. So it goes through 14 and 2. Yeah, that works as well. It goes through 4.75 and 11.25. Yeah, that one works as well, right? There's got a decimal in there. It also goes into the negatives. So if you have negative 20, or if you have 20 and negative 4, that one would work also. Okay, so all of these are going to work as a part of the pattern that is being shown. So you can use every single one, and that's why, again, we draw that line through with arrows at both ends, showing that it's going to continue going forever and ever. Yeah, in each way. Sorry, I should maybe go like that as it continues going. All right, so that's just, again, using what we know from context to create a linear equation to represent a pattern. And again, it's all about these patterns that we have. Now, let's look at a little bit at a system of equations. This is what we're going to focus on in our assignment today. What is a system of equations? Well, a system of equations represents two or more equations which are used to solve a problem. Okay, this is used when there are two or more scenarios which satisfy the relationship. So sometimes we are given like a few different scenario or a few different kind of aspects which are going to kind of limit what can happen in a relationship. And so there's a couple different equations that might come about. And I'm going to show an example of that in just a little bit. The two relationships are going to meet at a specific point. Okay, so this is where the lines meeting on a graph, they're going to meet at a point. This is a solution to the system. I'm going to show an example of it today, but I'm not going to get too much into it because we're going to go through a lot more of that in a future lesson as we look at how do we solve for these equations. Okay, or these types of situations. All right, so a system equation has two or more equations. Okay, so there's two or more limits to some context. And the answer to that is where the two lines are meeting on the graph. So they're going to cross somewhere on the graph, unless they're parallel lines, which then they never meet. But they're going to cross somewhere on the graph, and that's going to be our solution to our question. All right, So here's our question, the example I'm going to go through, and I'm going to try to go step by step, and I want to kind of give you an opportunity to see how we're going to describe it, and how we're going to solve for this one here. So we have the example we're going to give is a school division, which has two different sizes of buses. Okay. So now here in Hanover, we mostly have one big size of bus. It's a big bus, but maybe there's a division out there that has some big buses and some small buses. We're told that one of the buses can carry up to 30 passengers, so that would be the small one, and the other can carry 48 passengers. That would be the big one. And we're told that the division has a total of 35 buses and they can carry a maximum of 1,500 passengers. How many of each bus does the division have? All right, now we have two limiting factors here. Number one, we are told, okay, how many total students these buses can carry. And number two, we're told the total number of buses there are. Now, there could be lots of solutions to each one of these situations, but there will only be one solution which works in both cases. Okay, and again, that's where we're going to get to in the next lesson. But for this lesson right here, we're going to look at how do we come up with our equations to be able to solve, and then I'll just dabble with a little bit of the solving at the end. So the first thing that we need to do, and this is usually the first thing we need to do, is we got to figure out what are the variables that are at play here. What are the things we don't know? What are the things that are going to affect that the relationship is based upon? Well, we don't know, number one, how many large buses there are. It's somewhere between 0 and 35. Well, probably 1 and 34, but still, it's between 0 and 35, but we don't know exactly how many. We also, and this is related to it, don't know the number of small buses. So I'm going to use X as being the large buses and Y as being the small buses. If you want to flip that around, that's totally fine. Just know that on my examples, it's going to be X is large buses, Y is small buses. Now, this is important to know because when we are going to solve this and we're given a value of X and Y that make a solution, we have to know which one represents large buses and which one represents the small buses. Now, the next thing we need to do is to create an equation to represent the relationship. Now, here's the problem. There are two different things, okay? I put up the two fingers a few times, right? There's two different things which affect the number of buses. And because of that, we're going to have two equations which represent the two different limiting factors to our solution. So let's bring that up there and let's create an equation to represent the relationship. Oh, I popped that into number 3 already. Oh, sorry. That should still be number 2. The two things that we know that are going to limit the number or limit the relationship here and are going to give us hints as to how many buses we have in each. Number one, we know the total number of students is 1,500. So we need to look for a combination of buses which can hold a total of 1,500 students. Okay, that's a lot of students. And there is going to be a number of solutions which may work with that. Okay, and that's the important thing. We could have a number of different solutions to that. The second limiting factor, which is going to also affect how many buses there are, is that there are 35 buses in the division. So we know that we can't have more or less than 35 buses. We have to have exactly 35 buses to have this total of 1,500 students. Now, there is a number of different solutions to the first one. There are a number of different solutions to the second one, but of those solutions, only one of them is going to work for both. Okay, so as a little bit of an example here, let's say that there's 35 buses in the division. Well, you might say that there are 30 large buses and 5 small buses. Okay, 30 and 5. That works, right? 30 plus 5 is 35. So that could be a possible solution. But that solution may not have a total of 1,500 students. It might have more than 1,500 students. It might have less than 1,500 students. Okay, so there are solutions that work for one, but not for both. And that's where we need to find a solution for both. But before we can do that, we have to also get our equations in here, which are going to help us to solve for this. So the total number of students is equal to 1,500. We're going to create an equation where we have the total number of kids on the big buses plus the total number of kids on the small buses, and that's going to add together to be 1,500. Now, to get that, and we've talked about this in the past in my class here, we're going to say that 48 times x, So the number of big buses times 48, so that'll be the number of passengers on the big buses, plus 30 times y, so that's 30 times the number of small buses. So, right, our little small buses have 30 on them. That'll tell us the number of passengers on the small buses. When we add that all together, it needs to equal to 1,500 or 1,500. So that's our first equation. That's maybe a bit more of a tougher one, and maybe the reason why I did that one first as well. The second equation there, the 35 buses in the division, we should be able to know that that is x plus y is equal to 35. Okay, so x plus y equals 35. That's going to be our next one because we know that the number of large buses plus the number of small buses is equal to 35. All right, so here's our two equations. Now, for this lesson, this is more or less where we're going to stop. Okay, we're not really going to go too much farther. Next lesson, we're going to kind of add on to this and start solving. But when we graph these lines out, the intersection is the answer. Okay, so the intersection is the answer to that. All right, are we ready to take a look at that? So this is mostly where we're going to stop. We're going to talk domain and range in just a minute, but this is kind of where we would stop for this lesson here. But let's move it one step forward and look at the next one and how are we going to graph it out. So here's the graph of those two lines. Now, to be honest, I should really have them labeled, and maybe I'll try to do that in the notes later on Google Classroom. But here's our two lines, and you'll notice that they meet at the point 2510. That's important. So let's just go through the domain and range really quick. Domain and range, we know that they both have to be whole numbers. Okay, so they're both going to be whole numbers, which means that they are going to be positive numbers or zero, no decimals, no fractions, because you can't have part of a bus, you have to have full buses. And so our answer has to be like that, and it is. It's 25 and 10 are both whole numbers. They're both, we could say there's 25 large buses and 10 small buses. So with the graph, and I got to this a little bit already, you'll notice that meeting point. Remember that x is our large buses, so because the 25 is in x, that's going to be our large buses, and then 10 is our small buses because it's in y, and so our solution is that there are 25 large buses and 10 small buses. This is the only solution that's going to work for all the information that we're given. Any other solution, okay, might work for one or the other, but it's not going to work for both of them. This is the only one that works for both. All right, I hope you enjoyed this video. Hope that it's been informative and helpful. Okay, when you're looking through systems of equations, make sure that you create both equations, okay, the two equations, and make sure, again, you're defining your variables as you go through this because we need to make sure that we see those variables defined so we know what x and y represent. All right, all the best as you work through your stuff or through your questions. If you do have problems, feel free to send me an email or contact me, or you can talk to me in class when I'm around. Thank you very much. All the best.